Okay, howdy. I decided that we were just going to do a video for this lesson because honestly, you already have all the information that I need to tell you already, and I'm literally just going to reverse it from our last lesson. So I figured it would be easy enough for you to see a quick video of me talking about the math, and then we can go over. Look, I can move my little self. I'm over here now. So, filling in this blank, we all should have in front of us both this conditional statements sheet as well as the 3.3 proving lines parallel sheet. All right, so if we're looking at the 3.3 proving lines parallel sheet, you'll notice that right at the top, I've said theorem 3.4, converse of the corresponding angles theorem. So the corresponding angles theorem is actually something we covered in 3.2, right? That was that corresponding angles are congruent or equal to each other. Today, we're only going to be learning about the converse of each of our statements. So the first thing we have to talk about is, what does converse mean? All right, and I don't mean the sneakers. So let's go back to our conditional statements sheet here. There we go, conditional statements. All right, so when we talk about conditional statements, all right, conditional statements are going to be a statement that is true when read in one direction. All right, just one direction, not both ways, just one way. So I'm going to give you a very basic example of this. It's not like an official definition kind of answer to this, but a very basic answer. And if you have some highlighters or some colored pencils, grab those because we're going to talk about this and I'm going to highlight some stuff here. So example one here. If Ms. Nielsen is playing with her dog, then she is happy. So conditional statement, that's going to say that if I'm playing with my dog, I am happy. Now, is this the case 100% of the time? No, sometimes he jumps really hard and it's uncomfortable. But most of the time, this is pretty much true. So, the first part of this conditional statement is that I am playing with my dog. All right, no problems with that. The second part of my statement is that I am happy. All right, so if I'm playing with my dog, then I am happy. Is that true? Yes, absolutely. We're going to say yes, that's true. Absolutely, no problem. Oops, I'm covering my little check mark. I'll move myself down here. All right, if I'm playing with my dog, then I am happy. Let's see what happens when we reverse this. So instead of saying I am playing with my dog, then I am happy, I'm going to say if I am happy, I have to be playing with my dog. Now, I could be happy for lots of other reasons. Absolutely. I could be happy because I'm hanging out in math class. I could be happy because I'm hanging out with my sister. I could be happy because I went out for ramen. I could be happy for so many reasons, not just because I'm playing with my dog. So, is this a true statement? Is this a statement that always works for us? No, absolutely not. This is not always true. In fact, this is false. So, this is a statement that only works in one direction, right? So, this is what I mean by a statement, when true, that is true when read in one direction. Another example of this, if we want to bring it to math here, which I know we don't always want to do, but I gotta just to connect it back. I have to say, if a polygon is a square, then it has four sides of equal length. So is a square is the first half of my statement. Four sides of equal length is the second half of my statement. A square has to have four sides of equal length, so I have no problem saying that that is absolutely true all the time, right? No matter what, a square is going to have four sides of equal length. If a polygon has four sides of equal length, then it is a square. Now, you are absolutely could be thinking here in this moment, Ms. Nielsen, you're crazy. Equal sides has to be a square. Of course, this is going to be true both ways. What you just said doesn't work. But here's the trick. We are forgetting about one of our shapes, or a few of our shapes, right? So obviously, square, congruent, four sides, all of our angles have to be right angles in a square. But if we take something like, I don't know, let's say a rhombus, which we're going to cover a little later on, our angles are no longer all the same size. And I know that's wonky, but I'm doing my best here. all right? And so that is no longer a square, right? That's now a rhombus. So it is not always true. Sometimes it is false. And that is what we're talking about. Now, today's lesson, we're going to talk about biconditional statements. Everything that we talk about today is a biconditional statement, but I couldn't tell you about biconditional statements until we cover conditional statements. Biconditional statements are statements that are true in both directions. So we can read it either way. We can read either thing first and it will still be true, okay? If a quadrilateral is a rectangle, then it has 4 right angles. Absolutely. Quadrilateral is a rectangle, then it has 4 right angles, right? Rectangle has to have 4 right angles. We have no problem with this. This is true, no problem. All right. From here, if a quadrilateral has 4 right angles, then it is a rectangle. You might again be thinking, Ms. Nielsen, that's not always true. What about a square? And to that, I'm going to say a square is actually a rectangle. A rectangle is a much broader term for a square, right? A square is a very special case of one rectangle, all right? So that is what we are talking about when we talk about rectangle having 4 right angles all the time, all right? The other little example here is going to connect us into our lesson for today. If lines cut by a transversal are parallel, then the alternate interior angles are congruent. That is what we talked about yesterday. Absolutely, or in 3.2, which may have been yesterday, may have been a few days ago, depending on when you're watching this. All right. Now, the reverse of this in the opposite direction says that if alternate interior angles are congruent, then lines cut by a transversal are parallel. This is what we're going to talk about today and how this is true in both directions, no matter which way we flip-flop it. So let's flip ourselves over to this next page and talk about our theorems. Great news is most of what we're talking about is just about the theorems. So first thing, we covered what the word converse means. Absolutely no problems with that. Second thing, theorem 3.4, that means that we are in chapter 3. This is the 4th theorem that we're talking about. That is all that means. It doesn't mean that like it's section 3.4, because actually we're on section 3.3, right? So it says, if 2 lines in a transversal form corresponding angles that are congruent, then the 2 lines are parallel. This is just the reverse of the corresponding angles theorem that we talked about the other day in 3.2. So let's give ourselves an example. So let's label our angles here. We are told that if angles 2 and angle 6 are congruent, then we have to come up with the rest of that statement. I'm going to label my lines L and M because those are the best ones for some reason. They're always what we label them. It's always what your book labels them, right? We are told that angle 2 and angle 6 are congruent, so I'm putting my little curvy congruent marks here, right? Angle 2 and angle 6 are congruent. Then that means that line L is parallel to line M. No problems there, right? Same exact thing we said yesterday, just reversing it. Okay, so let's give ourselves an example then. We're going to label all of these lines. We are going to say that this is line A, this is line B, this is line L, this is line M. And then you're going to want to maybe take a second once I label all of my angles to copy them down here. So this is 3, 4, 5, 6, 2, 7. Nope, that's not 1. That's not 1. This is 1, and this is 8. All right? So these are all of the angles that we need to copy. Take a second, pause here if you need to, get that copy down. All right, and then what we are going to do is we are going to answer a couple questions here. So my first question to us is, which lines are parallel if angle 1 is congruent to angle 2? All right, so the question I'm asking is, if these are the two angles that are congruent, which lines are parallel? My recommendation, whenever we get something like this, is that we take a second and we cover up like the top half of our thing here. You see how I've got my little, that's all I have to worry about. I'm going to cover up that top half because we're not using those angles up there. We're only using the angles below. So now we can see, oh, M is my transversal. So 1 and 2 have to be corresponding angles. So the lines that are parallel, A is parallel to B. Yes, do we all agree that if I moved the pink square, we would have A and B is what they're labeled? Yes, cool, awesome. All right, second one. If I ask the question, which lines are parallel if angle 6 is congruent to angle 7, we're going to do the same exact thing we just did, except this time I am going to erase my little arc marks because I don't want to confuse anybody about what is congruent and what isn't. So this time we're focusing on angle 6 and angle 7. All right, we're looking at the green ones. If those two are the ones that we're calling congruent, cover up the rest of the paper. And actually, I'll write, this is L and this is M over here, just so that way we have it. Cover up the rest of your paper. Which are our two lines that are parallel? L and M. Okay? Can I delete you? Yes, I can. Awesome. So L is parallel to M. Awesome. No problem. That was the only example I had to get through. The rest of this is just going to be smooth sailing through the theorems, and then we're going to do 2 quick proofs at the end, and that is going to be it. You're going to hear the bell ring in just a second, so that'll be fun. Okay, so Theorem 3.5, converse of the alternate interior angles theorem, a theorem we've already discussed once again. All right, alternate interior angles theorem said the alternate interior angles were congruent. So no problems there. We absolutely know what that means. This is going to say the opposite, that because those angles are congruent, the two lines have to be parallel. There's the bell. No idea if you heard that or not, but fine. So this says, if angle 4 and angle 6 are congruent, then what? Well, first we have to know what angles 4 and 6 are, and those are going to be these alternate interior angles right here, which I am marking as being congruent, right? And as always, this is going to be line L and line M. So because angle 4 and angle 6 are congruent, then line L is parallel to line M. Done. No problem. Move on. .org. All right, flipping over to the back. This one says converse of the consecutive or same side interior angle postulate, which is the first postulate that we talked about the other day when we were talking about 3.2, which was that consecutive interior angles are supplementary when the lines cut by the transversal are parallel. This time we're flipping it around. So we say, if two lines in a transversal form consecutive or same side interior angles that are supplementary, then the two lines are parallel. So I'm going to flip over my notes key so that way I can write down exactly what I wrote down for myself earlier. But this is same side interior. So we're looking at the interior angles. So we are going to label this 3 and this 6. All right. And then this is still going to be L and this is still going to be M. Easy enough. So what they have told us, what they gave us as given information is that the measure of angle 3 and the measure of angle 6 is equal to 180 degrees, or they are supplementary, okay? Because of this, we can say that the L is parallel to M. Done. Move on. That is the theorem 3.6. Last theorem we have to talk about here today before I talk about 2 proofs, and then we are done for this video. Theorem 3.7 says the converse of the alternate interior angles theorem, alternate exterior angles theorem, alternate exterior angles, we were told, are congruent from our last note session. So when they're parallel lines. So I'm going to label this angle 1 and this angle 7. We are told that if angle 1 is is congruent to angle 7, right? So we are using our arc marks to demonstrate that they are congruent. This is line L, this is line M. Then the two lines are parallel. So line L is parallel to line M. Done. Theorem's done. Okay? Last things we have to do, these two really quick proofs. They don't look super quick, but I promise you that they are. The first one is a very simple 3 steps. The second one's a very simple 4 steps. And because I'm not having to ask you for the reasons, I'm just giving them to you, it's going to go by even faster than it does in class. So we are given that angles 4 and 5 are supplementary, and we are supposed to prove that line J is parallel to line K. So before we do that, we need to go in and label our things. That is line J and line K. We are going to label this here as 1, 2, 3, 4, 5, 6, 7, and 8. All right. So our first piece of information that we get just from the start is that angle 4 and angle 5 are supplementary angles. Right? I'm just abbreviating here just to make it fast. And we are told that information at the top. It is given to us. All right. Now, we have been given information that says that two things are supplementary. What does it mean for two things to be supplementary? We have to interpret the information that we have been given. Tell me what it means. Well, it means that the measure of angle 4 plus the measure of angle 5 is equal to 180 degrees. And this we can get by the definition of supplementary angles, right? Definition of supplementary angles, no problem with that. Last thing, we have proven that two things are supplementary. We've proven that their two angles add up to 180 degrees. These two angles add up to 180 degrees. Using that postulate, or that theorem, sorry, that we just learned, theorem 3.6, we can say, we can jump straight to J is parallel to K because of theorem 3.6, the I spelled things wrong, consecutive angles, right? Yes, consecutive angles. Oops, I am once again covering all of my little information. There we are. Consecutive angles, 3-step proof, easy as pie. All right, last thing, 2-column proof. We are given that angles 1 and 2 form a linear pair and angles 1 and 4 are supplementary, and we are supposed to prove that lines A and B are parallel. Now, before you just go writing whatever you want here and following the same pattern that I usually give, this pattern's a little different. Again, we're following what your book gives me, and I don't know why they changed it like this, but this is A and this is B, all right? And then the angles are 1, 2, 3, 4 this time, 5, 6, 7, 8. I am so sorry. That is really annoying. All right. But we can still use those same angle measures to figure out the parallel lines. All right. We can still use the angle measurements, relationships, not measurements. Oh my goodness. All right. So our first line should just be our given information, what we're given at the top. So we have to say that angle 1 and angle 2 form a linear pair. And then we also have to say that angle 1 and angle 4 are supplementary, right? And again, we can abbreviate as we need to, but this information comes to us because it was given to us by the proof, right? Whoever wrote this proof gave us this information. All right. So From here, let's interpret this information. We are told that angles 1 and 2 form a linear pair. That means that angles 1 and angle 2 are really supplementary angles, right? Because that's the definition of a linear pair. Excellent. Done. Definition of a linear pair. All right. Now, if you are thinking we need to change these things over to measurements and then add them together to show that they're 180 and then go from there and prove because of the transitive property that 1 and 4, 2 and 4 are equal, we would, if not for the fact that in Unit 2, Chapter 2, let's think back to our Chapter 2 notes, we had a theorem that said that if one angle and another angle are supplementary, and our original angle and a third angle are supplementary, then the angles 4 and 2 are supplementary. So I switched some stuff around there. 1 second. I was saying angle 1 and angle 4 are supplementary angles. Actually, I wanted to do that in a different color. Angle 4 are supplementary angles. Angle 1 and angle 2 are supplementary angles. So we can say that angle 2 is congruent to angle 4 because of theorem 2.2, which was the congruent supplements theorem back from chapter 2. This is to say that just because we have moved on from a unit does not mean it does not come back. It will absolutely come back. It will continue to come back. We should not forget about stuff just because it was in a past unit. All right. Now, we have said over here that angle 2 is congruent to angle 4. Hey, what type of angles are those? Corresponding angles, easily dealt with. We can just go in and we can say, hey, by the converse to the corresponding angles theorem, or theorem 3.4, the first theorem we talked about today, A is parallel, not to P, but to B. There we go. And that's in a little wonky of a spot. A is parallel to B. There we go. All right, so that is everything that is covered in this lesson. So apologies for a couple technical errors. This is the first time I've done it this way for geometry, but I think we got it all worked out in the end. I will see you all on the next class. I was going to say which day it is, but who knows? I'll reuse this in the future. So I will see you all in the next class, and please come with questions. We're going to be doing a ton of practice on this as your quiz is coming up very soon. Goodbye.